Hey guys, in this video we're going to take a minute and look at the difference between the two most common sensor designs, which are Whiskbroom and Pushbroom sensors. And although this is a little bit technical, the reason this matters is it can help you understand the limitations and the strengths and weaknesses of different satellite sensors, why they're doing things certain ways, and also can help you understand artifacts. As you start to encounter artifacts in your satellite images, understanding the way in which the sensor collected the data can be really helpful. So first, a few basic vocabulary terms of imaging systems or sensors. So the satellite is flying very, very rapidly along a linear track, right? And of course, it is sitting up above the Earth, and it is looking down at Earth. So we often will say the along track direction is the direction of flight. Okay, that's the direction the satellite's going. The cross track direction is perpendicular to that. The swath width is the total width that the sensor can image, okay, as it flies by, kind of on one flyby. And we often think of these satellites orbiting around Earth in laying down swaths or tracks of areas that they've imaged directly beneath them. So if you're working with a framing camera, the swath width might be equal to your instantaneous field of view. If you're working with a Whiskbroom or Pushbroom, the swath width is going to be larger than that instantaneous field of view. And another important idea is the dwell time. So this is the amount of time the camera shutter can stay open for each image, right? How long it can dwell on a specific pixel or image. So there's three basic types of imaging systems. One is a framing camera. I don't believe any modern sensor systems are actually really truly framing cameras, but it is a convenient starting point. Essentially, you've got your swath width and your instantaneous field of view are the same, right? Light from that surface comes up, goes through a lens or a set of imaging optics, and is projected back onto a image plane or a detector, right? And literally the size of that detector is one of the main things that governs the size of the field of view and the swath width, right? So it's kind of one-to-one swath width reflected back onto your detector. So another type, a second type, is a cross-track or a Whiskbroom scanner, okay? So essentially what this is, you can think of it as a single detector or like a single photosite, a single crystal of some kind, semiconductor crystal, that is grabbing photons. And instead of being a grid of photosites, what happens is there's a set of mirrors that actually scan across the track. So the satellite's moving very rapidly along the track, and this scanning mirror is going equally fast, bzz, 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 scanning that mirror and collecting photons from each pixel individually, and then sending them back to this point detector, essentially. So this has some advantages. The main advantage is you only have one detector to calibrate. So in terms of the electronics side of things, it's actually fairly simple, easy for me to say, simple to calibrate this detector. And typically you would also record many different wavelengths by just splitting a single beam of light through some kind of diffraction crystal or something like that. So you really have one detector or one detector per wavelength. The disadvantage is you have some moving parts. You have a rotating mirror, actually, that can break. It requires power. And also it may be slow as you have to scan back and forth. That may limit the pixel size that you can actually obtain. So an example of a cross-track scanner is Landsat 7. And actually famously, Landsat 7, I believe in 2013, the scan line corrector actually broke. And so if you encounter Landsat 7 images of a certain genre, you will see that they actually have a set of lines in the image from where the corrector broke. So the third category is a long track or Pushbroom scanner, okay? And this is, the analogy here is a Pushbroom like the big wide one that you would use to like clean out your garage, you know, where you just push it ahead of you forward instead of whisking it back and forth. And essentially what this is a linear array of CCD photo sites, okay? So this is more of a detector chip that we talked about in the previous video, where you have a bunch of photo sites right next to each other on a single chip. And as the satellite flies along the track, you collect the images in rows, basically. So you collect this row all together, this row all together, and so on. And so in this case, you know, your swath width is essentially equal to the instantaneous field of view, or at least the instantaneous width of the determined by this detector. So the advantages of this are because you don't have to move a single detector back and forth across the track, you can have a longer dwell time. You can collect each of those pixels kind of in parallel, and so you can sit on them for a little bit longer, which gives you a stronger signal and better signal-to-noise ratio. You also get geometric integrity. You don't have a moving part or a scanning mirror to deal with, essentially. And associated with that, you have less power demands, probably a longer lifetime because there's no moving parts. However, a potential disadvantage is that now that you have a row of, you know, whatever, 1,000 photo sites or more, each of those photo sites now is essentially its own detector. And they're all measuring light supposedly in the same way. But if you get any kind of electronic drift, then the photo sites could become miscalibrated from each other, and two photo sites that are measuring identical amounts of energy could actually record slightly different readings. So the cross-calibration becomes more of a challenge with these Pushbroom scanners. So a couple of the most famous Pushbroom scanners, the Aster sensor, which produced just an absolutely miraculous amount of data, was a Pushbroom scanner. And Landsat 8, currently operating, is a Pushbroom sensor as well. And, you know, when you compare Landsat 8, the Pushbroom, to Landsat 7, the Whiskbroom, you do see that Landsat 8 actually obtains a bit better spatial and spectral resolution, probably for a number of reasons, but partially because of its Pushbroom design. That's it, and thanks for listening.